All right, so let me go ahead and get into section 2.2, which gets at the intuitive definition of a limit. Okay, so in this section, we are going to utilize the notation quite a bit. So I really want to make sure that makes sense and you know how to read it. So look at this part right here. The way you read that is that the limit of f of x as x approaches a is L. So the limit of the function is L as x approaches a. Okay. All right. Now, part of what's kind of interesting is this first sentence right here reminds us that the function should be defined for x's that are near to a, but it doesn't necessarily have to be defined at a itself. So you could have a situation like this, where you have maybe a function that looks something like that. And so if this was our a value right here, the function may not be defined at a, but as you run along the function from the left, or if you run along the function from the right, it's approaching the same value. So the limit can still exist, even if the function is not defined right there. Okay. So if f of x gets as close to L as we'd like, arbitrarily close to L, for all x's that are pretty close, not necessarily equal to, but pretty close to a, then this is what we can say, that the limit of f of x would equal L as x approaches a. Okay, now I want you to begin looking at some of the issues. All right, remember how I'm going to be posting videos on rational functions and piecewise functions? The reason I'm doing it is they use them a lot as examples because they're interesting. For instance, this graph kind of looks like a cubic function, but then you've got these two holes, these two spots where it's not defined, and then it's defined otherwise at 2. This is a piecewise function right here. And it's also has a rational function component. So we'll do a little more with rational and piecewise functions, but I thought we'd jump right into the calculus of it all. Okay, so let's take a look. Here, I think is an important idea, making sure that you understand the difference between the value of the function at a spot and the limit of the function as x approaches that number. Okay, so this one, a, is dealing with an x of 1. Okay, so f of 1 you would find by just looking at the graph and seeing that the value of f of 1 would be 2. Now, to do the limit of the function as x approaches 1, you have to get kind of near 1, come from the right or from the left, and you can see you're approaching 2. Okay, so the value of the function at 1 and the limit of the function at 1 are the same. Okay, now look what happens on this next spot. Now we're looking at what happens around 2. So let's go to an x of 2. So the value of the function at 2 is way up here. It's 5. But the limit of the function as x approaches 2 would be found by considering this coming from the left or from the right. You see how you're approaching this spot, and even though the function's not defined there, the limit of the function would be 3. The limit of the function as x approaches 2, that would be 3. Okay. All right, now my pen does not write smoothly. I have to get it just right. All right, now let's look at an x of 3. So let me change to green for this one. Okay, so we're going to be over here focusing on 3. All right, f of 3 is undefined. Okay, nobody told us what it equaled. Okay, But as you approach 3 from the right and as you approach 3 from the left, you are approaching 4. So this would equal 4. Okay, so f of 3 is undefined, but the value of the function is undefined, but the limit of the function as x approaches 3 would equal 4. Okay. All right. Let's do a couple other ones of those. Get used to it. All right, so let's talk through this one. So we needed h of 2. So we go to 2, we hit the function. Okay, wait, that's an open circle. So h of 2 is not 3, it's 5. Okay. Now we want the limit of this function as x approaches 2. And I can see when I approach from the left or from the right, it's 3. Okay. All right, h of 4 is not defined. Okay, doesn't exist. Okay, the limit as x approaches 4 from the right or from the left, the limit would equal 1. And then the limit of h of x as x approaches 5, we would look right here, and whether you're coming from the left or right, it would equal, it would equal 2. Okay. All right, here's another example. And these little holes that you see with these other spots defined, sometimes like something like this is because of perhaps a rational function, and then they defined it piecewise. Here you have 3 different pieces. Okay, so piecewise and rational functions happen a lot. Okay, all right, let's look at number 4. All right, g of 0, so that's when you're right here, is 0. Okay, the limit of g of x as x approaches 0 is 1. G of 1 would be 2. G of 1 would be 2. And then the limit of g of x as x approaches 1 would also be 2. Okay? All right, now, we can't always graph things easily, and we don't always have a graph. So here's a situation I want you to think about. All right, so here we're being asked to make a conjecture, to guess what the limit of this function would be by looking at a table where we've explored what happens. So we're looking for the limit of the function as x approaches 1. So we're exploring what happens. So like if you imagine it, 1 would be here. You could imagine the 1 being there. This is the x and the y axis. So we're going to go to the right of that, and we're looking at, say, 1.1 to start with. Then we're going to get closer and closer to 1 from the positive side. So see, this pattern we use a lot. 1.1, 1.01, 001, 1.3 zeros and a 1. So we're getting really, really close to 1. Okay? And so you're just exploring this in here. What happens as you let your x values get closer and closer to 1 from the positive side. And then we do a similar thing. We come over here about 1/10 away from the other side, and we start looking at getting closer and closer to 1 from that side. So 0.9, 0.99, 0.9999. So we start about 1/10 away on either side, and then we move closer and closer together. All right, well, we can look at what somebody else has done and get a sense of what the limit of this function would be at 1 by considering that these are just slightly different from 1. Okay, you're just barely away from 1, 0.9999 and 1.001. Then you look at what you're getting and notice how both of them are getting really, really close to 0.5. So your conjecture would be that the limit would be 1/2 or 0.5. All right, now, before we move on from this, I want you to pause the video and I want you to try to type in 0.9 into that function. Let me make a little space here. Okay, so before you move on, pause the video and I want you to be sure you can that you can plug this in correctly, because these horizontal fraction bars are a bit of an issue. Okay, so when you're dealing with this on your calculator and you're trying to figure out limits using a table and you put in like 0.9 there, make sure you close the parenthesis, then subtract 1, then put in the 0.9 minus 1. This is harder to enter than you think. So I want to be sure that you catch on to a few things. Okay. First off, when you do this on your calculator, it gives you a left parenthesis. You have to be sure to close it before you subtract 1. Okay. And this is a grouping symbol, so be sure to put this in parentheses before you divide by the 0.9 minus 1, and it needs to be in parentheses. See, there's some understood grouping symbols here. Okay. So if you're going to try to enter these expressions, it does work well to have that in your calculator. And then as you're varying what the x is going to be, okay, what you do is you just adjust this. So this is already on the screen, so I can go back and just insert a 9 right here, or insert a 9 after that, and do 0.99 and hit enter, and then 0.999, so I can come back to that screen and just use my arrow keys and put an extra 9 at the end of all of those. Okay. Then I can, once I'm done with those, I can come back and put the 1.1 in there. Just use your insert and delete keys to help you with that. Okay. So just a couple things. This is a grouping symbol, means the whole numerator and the whole denominator need to be worked out. And when you do a square root, it gives you the left parenthesis. You have to be sure to close the right one before you subtract 1. Okay, so if you haven't yet, pause the video and try that. And if you did it right, it should turn out to be 0.5131670. Then after you do that, practice inserting an extra 9 in there without having to retype that whole thing, and that'll save you some work. Okay, and make sure you can get these. So try a couple of them. Try a couple and make sure you get those. Okay, once you've done that, come back and watch the rest of the video. All right, so here you're going to wind up working through these values. Okay. So you're going to go in, you're going to put in 1.9, 1.99, and so on. And again, watch the order of operations. And also, if these had been negative, be real careful about squaring, making sure what you plug in is in parentheses. Okay. All right. So we're trying to figure out a possible, what we think the limit might be of this function as x approaches 2. So see what we're doing? We're approaching 2 from the positive side, getting bigger and bigger. I mean, from the left side, getting bigger and bigger and bigger, approaching 2. Okay. And then we're going to the right of 2 and getting closer and closer to 2. Okay. So like 2.1 is here, 1.9 is here. So the top part of the table is doing that. Bottom part of the table is doing that. Okay. All right. So let's go ahead and be plugging those in and seeing what you get. Okay. So pause the video. Go ahead and be working those out. And then we'll come back and see what you're getting for those. Okay. All right, so you've come back to kind of see what we get. So we got a 3.9, then a 3.99, 3.999, and then 4 of them. And then down here we got like a 4.1, then a 4.01, then a 4.001, and then a 4.0001. Okay, when you type that in, make sure you did that extra grouping symbol. All right, so as we approached 2 from the right, we're getting closer and closer and closer to 4. And as we approach 2 from the left, we're getting closer and closer and closer to 4. So our conjecture would be that the limit as x of the function as x approaches 2 would be the number 4. Okay. All right, and then here we're going through and looking at the making tables to look at the limit as x as x gets closer and closer and closer to 0 from both the right and the left side. Okay, and so here's the 0. So we're looking at what happens when we're way out here, and then we're going to look at 0.001, and then 0.0001, and then 4 zeros. Okay, and then we're going to do the same over here. We're going to be out at negative 0.01, and then negative 0.001, and so on. Okay. All right, so what you do is you go in and you calculate those. So let's type that in. And on this one, the care you need to take is when you put in, say you're doing the 0.01 and then raising it to the 1 over 0.01, that doesn't really say that. You need to have this extra set of parentheses right here, okay? All right, so you can type in that. Okay, so this one turns out to be 2.70481. Okay, now go back up and just insert a 0, extra 0 in there. All right, and you get 2.71692. Okay, keep doing that same thing. We get a 2.71815 for this one. All right, and then we've got one more positive one to do. So take the time to do this if you weren't in class this morning. You really want to practice the calculator part of it. And then this one turns out to be 2.71827 if we round to 5 decimal places like they asked us to. All right, and then you can go in and just put, you're going to do 1, and it's going to be minus. All right, and then over there you're going to have a 1 divided by, and you're going to have a negative in there. Okay. And make sure some calculators, the negative and the minus sign are different. All right, but when I did that, this one with like the 4 zeros, this should have had a 4th 0. This one on the negative was 2.71883. Okay. 83. Yep. That was with 4 zeros. Okay. And then we could have done all the rest of these as well. So the idea is that whether you're to the right, let me double check my value. Four zeros. I lost count of my zeros. And this one was 2.71827. Okay, so these two right here are getting really close together. Notice if I've rounded to 4 decimal places, they would both be at 2.7183. And so these would be different things, but then what happens is both of these get really, really close to that 2.7183. Okay, so that's my conjecture, is that this appears to be 2.7183 perhaps. All right, and then they're asking a question, what constant does that appear to equal? And so this 2.7183 actually is an irrational number, kind of like pi. You know how pi is about 3.14? There's another irrational number we name and use a lot. You've used it in your pre-calculus, and that's E. And E is actually equal to, it's approximately equal to 2.7183. Okay, so the answer to this would be E. And if you have an E button on your calculator, you can do that and confirm it. My button is E raised to the X power. So you could do E raised to the first power and see that it turns out to be that 2.7183. Okay, actually that's the definition for E. So E is the number equal to the limit of this expression, 1 plus x raised to the 1 over x, as x approaches 0. Okay? All right, now the next thing we want to just formally talk about is that you can have limits that are just right-sided or left-sided. So the notation I want you to look at here. So f is defined for all x near a where x is bigger than a. So it's like you might have this function, and here's the a we're talking about. Okay, let me make a little hole at a, because a lot of times that'll be the case. So if f is defined for all x's near a when you're coming from the right side, and then f of x gets as close to L as we want when our x's get close to a from the right, then that L that we get is called the limit of the function as x approaches a from the positive side. So see how that positive is to the right of a? So if you're looking for the limit of f of x as x approaches a from the right side, a from the positive side, okay, and you're saying that's going to be your L, that's the right-sided limit. So you're doing this. You're coming in from the right. All right, the left-sided limit is f of x. The limit of f of x is as x approaches a from the left equals L. So same picture, but let me do it in blue. The idea is that we could be approaching that spot from here, from the left side. So the function needs to be defined for x's that get close to a. So again, the function would be defined for x's near a, not necessarily at a. And this little thing right here just means you're to the left. Your x's are to the left of a. Okay. And so if f of x gets arbitrarily close to L as we want, for x's that are getting close to a from the left side, then L is the limit of this function as x approaches a from the left. This one is a little trickier, the notation, because sometimes the a value will be a positive number and sometimes it will be a negative. So let me just show you what I mean. So let's say we're looking at x approaching 3 from the left. Okay, the limit of the function as x approaches 3 from the left versus the limit of a function as x approaches -3 are two different things, and you need to see the difference in it. Okay, so for this one, you should be focused on 3. And like if your function's doing something like that, you're looking at what happens as you approach 3 from the left side. Okay, coming into there. Okay, but you should be focused at 3. If you were doing this one, the one on the right, you actually should be looking over here at -3 and seeing what happens as you get close to -3 from either side. See how different those are? So get used to the notation. When you're looking at one-sided limits, the minus sign, the plus and the minus sign, they're after that a value. Okay. All right, so let's take a look. Here's a situation. Okay. And on this one, we're kind of getting an opportunity to see why a little bit of a review of some of the issues with rational functions can pay off. Okay, so here we're looking at a rational function. Okay, top part's cubic. We got a denominator. One of the things about rational functions is that if you have like x minus 2 in the denominator, a 2 would be a problem spot. If you put a 2 in there, then your function would be undefined at 2, right? Because you'd have division by 0. So f of x is undefined at x equals 2, because you can't have division by 0. Now, that factor of x minus 2 tells us that at 2, when we go to graph it, something interesting is going to happen. And the reason what happened is just a hole in the graph like that is because there's actually a factor of x minus 2 in that numerator. See, x to the third minus 8 is actually factorable into x minus 2 and then x squared plus 2x plus 4. Okay. And so because that numerator was factorable, and then I had this common factor of x minus 2, that x minus 2 could, in a sense, be canceled out, and I would fix the problem. So when we go and you look more at rational functions, wherever the function is undefined, you'll either have a hole or you might have something like this, where it's worse than a hole, where like your graph veers in one direction, veers in the other, and there's no way to bring those two pieces together. That's called an asymptote. That turns out to be a vertical asymptote. But if it's possible to fix the problem by just canceling out the common factor, then you just have a little bit of a hole there. Okay. So what they did is they're asking you for the limit of the function as x approaches 2 from the right, then do the limit as it approaches 2 from the left, and then just the limit of the function as x approaches 2 in general. And what they were reminding you of is if you use a graphing calculator or a computer to graph, you're not necessarily going to see a hole. It's too small scale. Okay, so your graph might look like this, but it's actually not defined really at 2. So you have to use a little of your knowledge of rational functions to get this picture right. Okay, so as you approach 2 from the right, the limit seems to be, see how it's approaching 3? As you approach 2 from the left, getting bigger and bigger and bigger, getting closer and closer and closer to 2, the value of the function is getting closer and closer and closer to 3. And then the limit of the function at 2 would be 3 as well. Okay. All right, now this result we use a lot to decide whether or not a limit exists. Okay. All right, if and only if is like an equal sign that goes both ways. Okay. So, your function, we got to assume the function's defined for x is near a, not necessarily at a. Okay. So what we're saying is the limit of f of x as x approaches a would equal L if and only if these exist. These are true. The limit as x approaches a from the positive side and the limit as x approaches a from the negative side both equal L. Okay? And so this if and only if, sometimes we write it like that, is really a two-sided arrow. It says, if this is true, then we know each of the two-sided limits must both equal L. And then it also says, if each of the two-sided limits equal L, then you know that the overall limit would be L. So it goes both ways. Okay? So let's look at this problem. All right. All right, so this example, the graph of it is kind of interesting. And I can kind of explain why a little bit. But the reason this graph looks the way it does is that numerator can be factored. If you factor, let me see if I can get the pen to write better. If you can factor out a 2, okay, we do it up here. If you factor out the 2, you'll have x squared minus 3x plus 2 left. And then that could factor into x minus 2 and x minus 1. So see how there's an x minus 1 down here and an x minus 1 up there? Here's the thing. There's an absolute value around that x minus 1 in the denominator. Had that just been 2, and I'm going to go ahead and write the factored form, had it just been this, gosh, sorry. Get that pen fixed. Without the absolute value, then see how that common factor could be canceled out, and your function would have just been this 2 times x minus 2, which is just the line y equals 2x minus 4. Okay? And so that's what this is right here. This would be the line y equals 2x minus 4. It would start at -4 and then have a slope of 2. All right, the thing is, that's not just x minus 1. That's the absolute value of x minus 1. So this g function would equal this right here, this what I'm getting, okay, if x minus 1, the part inside there, were bigger than 0. And so if x minus 1 were bigger than 0, then the denominator would just be x minus 1. This would hold true. And x minus 1 bigger than 0 means x is bigger than 1. So do you see how that graph was only used when you were bigger than 1? That's why. Okay? And then at 1, it's not really defined, is it? Right? Because it would make division by 0. So that's why there's an open circle. All right? Now, what happens over here happens because if this x minus 1 is less than 0, if x is less than 1, that would make x minus 1 less than 0. It would make it, less than 1. If x minus 1 is less than 0, then x would be less than 1. All right, and if x minus 1 were less than 0, that would mean you'd have a negative inside there. And so absolute value would turn it into a positive. So if you're on this side, so if you're where x minus 1 is less than 0, then this right here that you had before, to try to rewrite it with that absolute value, you would have to do the opposite of what's down there. So the x minus 1 could still be canceled, but you'd still have the negative. It would turn out to be negative 2x times the quantity x minus 2. It would turn out to be negative 2x plus 4. And see, that would be this line. Okay. But you're only supposed to use that line when you're less than 1. So that's over here. And it's still not defined at 1. So this kind of talk and work that we're doing, this was actually sort of like a rational function, except for it's actually a composition of functions. You've got the absolute value down there as well, so it makes it even harder. Okay. All right, so that's where that graph came from. If they give you the graph, you don't really have to go through all of that. You can just look at your graph. All right, so let's consider the 3 things they asked us for. What's the limit of the function as x approaches 1 from the negative side? Okay, then the limit of the function as x approaches 1 from the positive side, from the right side. And then overall, what's the limit of the function? And here's where we're going to use the theorem. Okay. All right, so if you approach 1 from the negative side, then the function values approach 2. Okay. If you approach x, if you let x approach 1 from the positive side, then your function values, right, then you're going to come in and they're going to go towards -2. And then because these aren't the same, then the limit of the function at 1 itself does not exist because it didn't turn out to be the same. All right, so remember the if and only if statement. Okay. These would have to both be the same in order for the limit to exist. All right, so here's another graph, and here we got that notation about right and left-sided limits. We also have just pure function notation. So g of 2, see how g of 2, you wouldn't stop there, you'd go to the closed-in dot, should equal 3. The limit of the function as x approaches 2 from the negative side, you should pause this and do the problem and then come back and check yourself. The limit of the function as x approaches 2 from the negative side would be 2. The limit of the function as x approaches 2 from the positive side would be 3. So the limit of the function at 2 does not exist because the two-sided limits don't equal the same thing. The left and the right side limits don't equal the same. All right, let's move on to 3. G of 3 would be 2. So g of 3 would be 2. A limit of g as x approaches 3 from the left would be 3. The limit of the function as x approaches 3 from the right would be 2. And if they had asked me, the limit of g of x as x approaches 3 would not exist. Okay. Now let's look at g of 4. G of 4 would be 3. The limit of the function as x approaches 4 would equal 3 as well, because whether you go from the left side or the right side, you wind up getting that to equal 3. Okay. All right, now I want to look at number 19 and number 21 and just kind of make a comment about this. You'll get a little more practice on graphing these. These are piecewise functions that you're trying to sketch the graph of because it'll help you to make conjectures about what the limits would be. And so when you're doing these, okay, you've got these 2 rules. One of them on that first problem, you use when your x's are less than -1, and then you use the bottom rule when x is bigger than -1. And the a equals -1, that comes into play after we have the graph. We're going to consider the 3 limits. All right, so to do a graph, here's kind of what you should think. You think about being over here at -1, that when you're to the right of this spot right here, you're going to use the rule that the output equals 3, that the y value, this is really y, that y equals 3. When you're to the left of -1, you're going to use the rule that y equals x squared plus 1. Okay? And so y equals 3 would be a horizontal line, right? Y equals x squared plus 1 would be a parabola. So y equal 3, I'm supposed to use that when I'm over to the right of this. So it's going to be what I use when I'm over this way. And then see how it doesn't have the or equal to? So that makes you put an open circle on that. And then when I'm over here to the left, I'm supposed to use y equals x squared plus 1. And I know that's a parabola. I know it's up 1 on the right there on the y-axis, but sometimes I just like to know it's a parabola and then find out, well, what does it do right at -1? And don't forget to square that. Put it in parentheses and square that. That's +1 plus 1. So you get 2. And then I'm going to get another point. If I put in a -2 and square it and add 1, I'd get 5. So I'll sometimes do that to get a pretty good picture. Let me do this piece in red. So when x was -1, that piece of the function was 2. And then -2 was up at 1, 2, 3, 4, 5. And it's not linear. It's more of a parabola. So just draw it so it looks kind of like a U. And keeps going. And then at -1, this was the one I was supposed to use. So let me emphasize that that's a closed circle right there. Okay. All right. Now, if you have the graph, then you can do the limit of the function as x approaches -1. Now watch it. It's approaching -1 from the negative side. Then we're going to do the limit of the function as x approaches -1 from the positive side, and then we'll consider the overall limit of f of x as x approaches -1. Okay. All right, so the limit of f of x as x approaches -1 from the negative side would be 2. But the limit, that should be up a little higher. It's like right there, equals 2. Then the limit of the function as x approaches -1 from the positive side equals 3. And because these are different, this one does not exist. Okay. All right. And then let's look at an application problem that's pretty common. Postal rates. The cost of mailing letters and packages actually are piecewise functions that are kind of a special type. They're called step functions. And it has to do with this up to and including, this up to and including part here. All right, so here, let's go ahead and get a picture. They want us to get a picture of what this would look like for packages that weigh or letters that weigh from 0 to 3.5 ounces. So let me emphasize the first quadrant. This is W. This is the postage rate. Okay, so let me do 1, 2, 3, 4. And let's get a little table going here. Oops, not X, Y, it's WP. W and P. And let's just get some data in there. So if the letter weighed 1 ounce, then it would cost us 47 cents. Okay. If it weighed 2 ounces, then we'd pay 47 for the first ounce, and then we'd pay only 21 cents for the second one. So that would be 68. And if we went up to 3 ounces, we'd have to pay another 21 cents on top of that, wouldn't we? So that would be 89 cents. Okay, so let me go ahead and make the graph easy for us to do. So let me put 0.47 and then have it go up 21 cents after that. All right, so 1 ounce, 47 cents. 2 ounces, 68 cents. 3 ounces, 89 cents. If I did 4 ounces, it'd be $1.10, wouldn't it? Okay. But just having a line connecting those doesn't really convey what's really going on. So let's go ahead and put in some half ounces. So what if in here we had a 0.5, a half of an ounce? Okay, you spend 47 cents for the first ounce up to and including 1 ounce. Okay, so up to and including 1, you pay 47 cents. So that means at a half, you'd still pay 47 cents. If it was 0.1 ounce, you'd still pay 47 cents. So you're going to pay 47 cents up to and including something with 1 ounce. All right, and then like say you go over the 1 and you go to 1.2 ounces. Okay, you'd pay 47 for the first ounce, and then you'd pay 21 cents. Sometimes they say it this way, for each additional ounce or part thereof. Okay, so for that extra little piece, you're still going to have to pay 21 cents. So 1.2 would still be up here at 68. Anything just past 1 all the way to 2 would be 68. Open circle on this end, closed circle on that end. Okay, 2.5, same deal. If you went to 2.5, you'd pay an extra 21 cents. And so this would be open, go to here, closed. Okay, open, go to here, closed. All right, that's called a step function. And sometimes the steps have the same length, sometimes they don't. Like sometimes it would be things like 47 cents for the first 2 ounces, and then 21 cents for every additional ounce after that. So sometimes it can vary. All right, so this is a pretty good picture of it. So we can use this to look at what would the limit of the function be as W approaches 2.3. So here's 2.3, somewhere in here. And we can see whether you come from the left or right, it's going to be the same thing, and it's going to be up there at 0.89, 89 cents. Okay. But then notice this question. The limit of the function as the weight approaches 3 doesn't exist, does it? See that spot? Because you'd get $1.10 from one, and you'd get 89 from the other direction. So it does not exist because the right and the left-sided limits aren't the same. Okay. All right. Now, this last one, I just wanted you to see that there are things where a graph and a table really are almost still not adequate to feel positive about what you think the limit would be. So if we were going to make a conjecture about the limit as x approaches 0 of cosine of 1 over x, we might just plug in, we might start by looking at being to the right of 0 and getting closer and closer and closer to 0 and seeing what happened. And if we stop too soon, we might say, oh, it looks like it's approaching -1. But then we go even closer and we're back to almost +1. Something really weird happened right there. So I was thinking it was going towards -1, and then all of a sudden it jumped, and now I'm at +1. And then look, I'm again at -1. You know, it's doing something kind of weird. All right, I want to remind you first off just about the basics of the cosine graph. Okay, so remember when you're trying to graph cosine, you can think about the unit circle and think about these 4 key points right here. Sometimes we call them 5 because we come back around twice. That's 0, it's pi over 2, that's pi, 3 pi over 2. And just knowing what the coordinates of those points are at each of those spots actually is giving you the sine and the cosine. Okay. All right, so if I were to graph just y equals cosine x, which is not what I'm being asked to do, Okay, that function would fluctuate between 1 and -1. See, when you're at 0, cosine, remember, is the x coordinate of those points. You'd be up at 1. When you get to pi over 2, you're at 0. When you get to pi, the cosine value is -1. Then when you get to 3 pi over 2, you're back to 0. And then you get to 2 pi, and you're back up at 1. And cosine is the one that starts at 1 and then does this. You can keep going. Or does that. You can keep going there. Okay? All right, now, so to analyze this, what they did, I just wanted to kind of talk through it, but you can read it too later, is they said, you know what, let's go ahead and analyze specific spots on this. Let's make the 1 over x turn out to be something that we know the value of easily. And so they made a substitution. They let this inside here turn into cosine n pi by making a substitution. They plugged for x, they plugged 1 over n pi in, which then turned the problem into cosine of n pi. It's just kind of rewriting it so you can think about it and try to understand better what's happening. They did that because you already know this. If you have cosine of 1 pi, you're here, and the cosine would be -1. If you have the cosine of 2 pi, you're all the way to here, and the cosine would be +1. So, okay. And then if you go around to 3 pi, you're back over to here, so you're back at -1. And if you go to 4 pi, you're back over to here, okay? So when n is 2 or 4 or 6, you're going to be up at +1. And so they're just saying, you know, just by looking at, okay, that substitution they made and then using it, they were able to try to get you to see what's really happening. So this function winds up fluctuating as you put in the 1 over some integer times pi. The graph winds up fluctuating from 1 to -1 to 1 to -1 as that denominator goes from 2 pi to 3 pi to 4 pi to 5 pi. See how you're jumping? Okay. And as you do make that denominator bigger and bigger and bigger, it's getting closer and closer to 0. But as it goes, it's jumping from positive to negative, positive, negative, positive, -1. And so just the limit approaching 0 from the positive side doesn't exist because it's jumping from 1 to -1. Okay. All right. So that's the some of the information that was in section 2.2. Just wanted to kind of go through and explain that. I'm going to go ahead and post this, but I'm also going to work on post this video, but I'm also going to go back and fill in, make sure the videos are posted for rational functions and for piecewise functions.